Radio astronomy had reached a steady working age. Dishes and antennas listened day and night, turning the sky into a stream of numbers that could be checked and rechecked. Over time, a pattern held. Most radio sources stayed put in their behavior, galaxies, nebulae, and pulsars that rose and fell in predictable ways. The sky felt reliable. That reliability shaped expectations. The problem was that the universe also produced brief radio flashes, signals that appeared, peaked, and vanished before anyone knew to pay attention. These transients did not politely repeat on schedule. They arrived without warning, sometimes lasting less than a blink in the data. A telescope could be pointed elsewhere. A computer filter could reject it as noise. One missed moment could erase the evidence. So the field relied on constant monitoring and ruthless triage. Software searched the flood of measurements for anything that broke the rules. Too bright, too fast, too out of place. But even with mature instruments, the odds stayed uneven. Steady sources dominated the sky, and rare bursts hid in the gaps, between scans, between thresholds, between assumptions. That was how a real signal could slip past, until it did not. The first sign of trouble did not come from a person staring at a screen. It came from the survey telescope's data pipeline, a piece of software built to sift through huge streams of raw radio noise and pull out anything that looked like a real burst. In that flood, it flagged a sharp spike. It lasted only a moment, but it stood out. The coordinates pointed to a patch of sky with no known radio source recorded there. That detail changed everything. If the signal had matched a catalogued object, it could have been filed as expected behavior. Instead, it appeared to come from nowhere. The pipeline treated it as a candidate event, not a discovery, because false alarms happened all the time. A stray glitch in the instrument could mimic a burst. So the team went back to basics. They checked the timestamp, the frequency range, and whether the shape looked like real sky emission or simple interference. They compared the burst against lists of known transmitters and against the telescope's own logs for hardware issues. They asked a blunt question. Did anything else break at that exact moment? They also searched nearby observations to see if the same patch of sky had shown even a hint of activity before. Nothing obvious answered back. The event stayed in the system as an anomaly, and that label carried weight. It meant the next step could not be routine. It required immediate scrutiny. The first burst did not get filed away and forgotten. It triggered a basic question. Did anything else happen in that same place, just outside the moment the software had noticed? The team went back through the recent data, stepping minute by minute, then widening the window. What looked like a single spike started to feel less lonely. Another small burst appeared. Then another. Now the pattern mattered. These were not random blips sprinkled across the sky. The bursts lined up with the same patch, separated by stretches of silence, then sudden returns. That changed the risk. A one-off event could be a fluke, a glitch, a stray bit of interference that slipped through. But a repeat from the same direction across hours demanded attention. It acted like a source. With each extra hit, confidence rose in one way and pressure rose in another. The pipeline had not just stumbled onto an odd shape in the noise, it had pointed to something that came back. The team shifted from questioning the detection to tracking the behavior. When did it fire again? How strong was it this time? The mystery moved up the priority list fast. The bursts did not fade away after that first strange stretch of hours. They came back the next day, and the day after. Each time the instruments caught the same kind of sharp radio flash from the same region of sky, it shifted the problem. A fluke could still happen once, but a pattern over days demanded attention. Now the teams treated it like a source, something that could be tracked. With more repeats, the measurements tightened. Astronomers marked the exact arrival times of each burst, then compared them, looking for any clockwork rhythm hiding in the gaps. They also measured brightness more carefully because one strong detection could mislead, while many detections revealed a true range. Some bursts landed hard, others came in weak. That spread itself became a clue, not noise. The frequency structure finally became something they could trust. A single event could look distorted by chance or by the equipment, but repeated bursts let them line up the data and see what stayed the same. They checked how the signal's energy spread across the radio band, which parts lit up and which stayed quiet. The more it repeated, the less it looked like a glitch. It looked like behavior. With days of bursts in hand, the team stopped asking only how often it flashed and started asking what happened to it on the way here. The burst arrived smeared out across frequencies, with the higher notes coming first and the lower notes lagging behind. That delay mattered. It matched what radio waves did when they passed through ionized gas, a thin fog of free electrons spread through space. The size of that delay worked like a crude yardstick. The more electrons the signal crossed, the more it got stretched in time. The numbers did not fit a path through just Earth's atmosphere, or even a small pocket of nearby plasma. They implied a long journey through a lot of ionized material. And that pushed the source outward, away from the comfortable idea of something local and ordinary. Then there was scattering. Instead of a clean, sharp snap, each burst showed a slight tail, as if the wave got jostled and took multiple paths before reaching the telescope. That kind of blur happened when radio passed through turbulent plasma, not pristine empty space. Put dispersion and scattering together, and the signal looked processed by distance. A nearby glitch still stayed possible, but it started to look less and less believable. With the distance clues looking hard to fake, the next question sounded almost simple. Was the signal real, or was it just a trick of one telescope? Teams moved fast to check. They asked other observatories to watch the same sky position, using different receivers and different software. If the bursts came from local interference, they should have vanished when the equipment changed. They did not vanish. Other instruments picked up bursts at the same place on the sky, with the same kind of frequency sweep and the same abrupt on and off behavior. The timing never matched the schedule of one facility or the quirks of one pipeline, and the signal did not track any obvious change in local conditions. That repeatability across independent systems raised the stakes. Each new detection acted like a cross-check. Different telescopes meant different electronics, different interference environments, and different ways to process the raw data. Yet the pattern kept returning, stubbornly consistent. The chances of a single local glitch started to shrink, detection by detection. What remained was uncomfortable and exciting. Whatever produced these bursts behaved like a real source in the sky. With the repeats confirmed, the next step sounded simple. Find the obvious culprit. Scientists checked whether the bursts lined up with aircraft routes because planes carried strong radios and moved fast enough to fool a telescope. The times did not match. They compared the detections against satellite passes, including the busy bands used for communications. The signal arrived when no tracked object crossed that patch of sky. Then the teams turned inward, suspicious of their own tools. They audited cables, receivers, clocks, and recording computers, hunting for a glitch that fired in bursts. They searched for local electronics that could leak interference in a repeating pattern. The behavior stayed the same across different instruments and different observing sessions. A malfunction could mimic one event. It struggled to imitate days of consistent structure. Next came the familiar sky explanations. Pulsars already flashed like cosmic lighthouses, so the timing was tested against known spin patterns and harmonics. It did not lock to any stable period the way pulsars usually did, and its frequency sweep did not fit the standard templates. One by one, the easy answers fell away. What remained was a narrower question. What kind of object kept producing bursts like this? With the obvious explanation stripped away, the problem changed shape. It no longer sounded like a glitch that fooled a computer or a passing transmitter that slipped through the filters. It behaved like an object in space that could switch on, fire, and go quiet again. And one idea began to fit better than the rest. A neutron star, the crushed core of a dead star, but not an ordinary one, a highly magnetized neutron star. In this scenario, the key was the magnetic field. Some neutron stars carried fields so intense they stored huge amounts of energy, then released it in sudden, violent changes. When that magnetic stress shifted, it could jolt the star's surroundings and drive a burst of radio waves. Not a smooth beacon, but sharp flashes. That matched what the instruments recorded, brief spikes, repeated, with enough power to be noticed far away. The repeating pattern no longer looked random for no reason. A magnetized neutron star could flare in clusters, then settle, then flare again, depending on how its magnetic system rearranged itself. The signal structure also made sense in that light. A compact source, producing fast bursts, with the details shaped as the waves pushed through gas on their way out. The mystery narrowed. A living, active remnant of a star became the front-running suspect. The magnetized neutron star idea explained how bursts could be made. It did not automatically explain the strangest scheduling detail. The way the signal seemed to wake up, fire repeatedly, then go quiet again for days. That pattern pushed scientists toward a second possibility. Maybe the source was not changing at all. Maybe something between it and Earth acted like a switch, shaping what the telescopes actually received. One explanation pointed to the source's own neighborhood. If the object sat in a binary system or inside a clumpy wind of gas, an orbit could regularly carry radio waves through thicker material. Some days the path stayed clear and bursts arrived easily. Other days the same bursts got blocked, scattered, or absorbed before they escaped. The repeating window then came from geometry and timing, not from the engine turning on and off. Another explanation reached farther out: plasma lensing. Ionized gas in space did not just delay radio waves, it also bent them like a moving lens. A dense patch could briefly focus the signal toward Earth, making bursts look brighter and more frequent, then drifted away and let the source fade below detection. That meant the days-long rhythm could have been an illusion created by the space in between, not the object itself. By the time the days-long repeats were accepted as real, the question shifted. It stopped being, was this a fluke, and became, what else was out there? More surveys went looking on purpose, and they kept finding new repeaters. What once felt like a single impossible case started to look like a population. The shock faded, replaced by a new routine. Catch the bursts, log them, compare them, and wait for patterns to show up. The biggest change came from precision. Instruments and software improved enough to pin these bursts to much smaller areas of sky, sometimes to a particular galaxy, not just a vague direction. That better localization turned guesses into tests. It let teams connect repeats to their surroundings and track how the signals changed with time and frequency. Instead of chasing a ghost, astronomers built catalogues, measured rates, and sorted repeaters by how regular, how clustered, and how bright they were. With more examples, the explanations expanded. Magnetized neutron stars stayed central, but they no longer had to do all the work alone. Some repeaters fit violent outbursts. Others matched signals shaped by motion or by plasma acting like a shifting lens in space. The field matured into competing natural models checked against growing data. And that early event, the one that repeated for days from nowhere, ended as a starting line for modern understanding.